All right. So in this lecture, we're going to talk about sampling distributions. So let's get started. Now, the first thing we need to understand is the difference between a population and a sample. So a population is basically the entire group of something that you want to draw a conclusion about. So for example, if you want to know the the average height of every human on Earth, right? So our population is all of the humans on Earth. Now, if I were to pick 10 random people, 10 random humans, right, that would be a sample. A sample is basically a subset of the population, or basically a group of random people from a population, right? And similarly, this example could apply to anything else. Like, for example, uh, if you want to know how many cars have a horsepower of above 100, maybe, so in that case, your population would be all of the cars, perhaps all the cars of every brand. And then maybe if you take 10 uh, random cars, or maybe if you take all of the Honda cars, that would be a sample of this population because it's all encompassing. So hopefully that makes sense. Now, moving on, uh, we have parameters and statistics. So, basically, a parameter is something that describes a certain aspect of the entire population. So, for example, uh, the average height of every single human being, right? So, which we could also say is the mean height of all the human beings of the whole population. So, that uh, this mean is basically a parameter. It's something that's describing the property of the whole population, right? And similarly, if we were to take a random sample of 10 people and we compute the mean of those people's heights, we get a sample mean, right? Or a sample statistic. They're basically quantities that describe the property of something, but a parameter applies to the whole population, is a number that describes a property of the whole population, whereas a sample statistic applies to the sample. And similarly, a standard deviation could be a parameter, a proportion could be a parameter, size could be a parameter, right? And here's the common convention. So for population, we denote the mean as the symbol mu. And for a sample, that mean is represented usually by an x bar. Standard deviation, we have sigma, and we have s here. For proportion, we have p for population and p hat for the sample. And size, we have capital N for population typically, and small n for the size of a sample. So it's good to remember these because oftentimes you might get a question or something that gives you X bar, and you might be wondering what an X bar is. So like it's good to remember these. All right. So let's start with a simple example. So we're interested in finding the age of all GW students. So we take a random sample of 300 students and find out that their mean age, which is by the way donated by X bar, is 22, right? So in this case, what is our population, right? So, I mean, I'd encourage you to think about this for a second. So, yeah, so our population would be all of our GW students, right? There we go. And what are we interested in finding? Uh, we're interested in finding the mean age of all of the GW students. There we go. All right. So, next thing is suppose that we had 600 students in total, right? Meaning that the population is 600. What does the sample mean of 22 tell us, right? So the sample mean, we've taken 300 students out of the 600 and we've calculated their mean age. So do you think that the number 22, which is the mean of 300 students, does that tell us something about the mean of all of the students, this all 600 students? That's basically what the question is trying to ask you. So, so you might be thinking, right? Like, uh, the mean of 300 students is 22. What does that make you think about 600 students? What it tells us is that, you know, intuitively we might think that 600 for 600 students the mean may not exactly be 22, but it might be something close to 22, right? So yeah, it gives us a fair estimate of the population slash true mean, which is another word used for the population mean, the parameter. We can expect the true mean to be around 22, but probably not exactly 22, right? So why do we, why do we use samples? So let's say we were trying to calculate the mean age of every single GW student, or the mean age of every human being on Earth, right? We To get an accurate measure of that, we would have to find out the age of every single human being, which is more than 7 billion. We need to get their ages, and then we need to take the mean of that. And in reality, doing that is something very difficult because it's very difficult to get accurate data on every single human on Earth. Populations tend to be large. Uh, and that's why we end up taking samples. And samples are a way to approximate uh, a parameter of a population, right? Uh, and what we're going to basically talk about here is what's the best way to get an approximation, and how do you know how accurate your approximation is going to be, right? So here I took a sample of 5 GW students, right? And I got their mean age to be 22. Uh, this sample could may as well be the actual mean age of all the GW students, but it could also be very far from it. Maybe every other GW student was age 26 or above, right? So our population mean is going to be 20 around 26 or something, but not 22, so it's not very representative. So we're going to talk about how we can be uh, confident about what our mean is, and what things we can do to ensure that basically our approximation is controlled and we know what we're doing. Right. So that brings us to sampling variability, right? So sampling variability, it's basically the idea that our sample mean will vary depending on what sample we choose, right? So like over here I mentioned, like maybe if everyone else was age 26 or more, this sample is not very accurate, which is an unlikely scenario, but it can still happen. So look at this picture, for example. Uh, we took a sample here from this population of numbers. We got 31975. It has a certain mean, right? Uh, which is perhaps a good approximation of this whole mean. But if you think about it, what if we selected 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5 would have a mean of 3, which would perhaps not be as good of a representation of the population, right? So uh, it depends on the sample that we choose. And another thing that the sampling variability depends on is the size of the sample. So if we were to choose a sample of 7 numbers, right? 7 numbers would only leave us with one number that we haven't chosen. So it's something uh, closer to the population size, or the larger your sample is, the less variability there's going to be. Because think about it, uh, if we take 7 numbers, there's there's only there's only a certain number of ways that you can select this sample, right? And your sample is gonna cover or encompass uh, most of the population, right? It's gonna be a good representation of the population. So there's only limited variability in that case. There's also a concept that relates to the law of larger numbers. So you could look that up more if you want to learn more about that. But moving on, let us look at this example real quick, right? So let's say we had an island X where only 4 people lived, and we want to find uh, right. We want to find uh, we want to find the population mean of their net worth, right? So in this case, I made a very simple example of a population of just 4 people, so we can quickly work out the population mean, know what that is exactly. Uh, yeah, so know what that is exactly, and that works out to 30, right? So we add all the numbers, divide by 4, we get 30, right? So So now let's for a second imagine we weren't able to calculate the population mean. Let's say if we took a sample of two people out of these four people. So uh, what are all the different ways we can take two samples, right? So we can take AB, we can take AC, AD, BC, BD, CD. So there are six possible samples of size 2 that we could take, six different samples. Uh, and you could get this number by doing 4 choose 2 using combinatorics, but I laid them out just so it's more easier that way. So the mean of A and B is 20 plus 10 is 15. For A and C is 20 plus 40. 20 plus 40 divided by 2 is 30. Similarly for AD, we got 20 and 50 got 35, BC 25, BD 30, CD 45. So we have all these different means, all these different sample means, right? Of every possible sample of size 2 of this population, right? So what is the average, right? What is the average what is the average value of every single sample? So we add them up, divide by 6, and we get 30, which is the same as our population mean, right? And you might be thinking it's a coincidence, right? But I'll get to this in more detail, but short answer is that it's not a coincidence, and we're gonna learn that so basically the mean of every single sample, every single possible sample of a certain size ends up being the same as the population mean, right? And that brings us to sampling distribution. So what we were talking about right now, right? We took the mean uh, of every single sample, right? So what we have here is we have one sample of size 15, we have one sample of size 25, we have two samples of size 30, one sample of size uh, 35, and one sample of the mean 45. So this distribution, or this sample to frequency ratio, is actually called a sampling distribution. So similarly in that picture, or maybe I can just draw it out for you here, right? Uh, sorry. So we have one sample of size 15, right? 15. We got one sample here, and for, let me go back and see. For 25, we have another sample of size 1. So don't mind the different sizes. And we have two samples of size 30, right? So this is 1. So we got two samples of size 30. So two samples there, two samples of size 30. And we got one sample of size 35, one sample of size 45. So again, one sample of size 35, one sample of size 45, right? So that's our distribution, right? And for maybe a larger sample, we get a distribution that's more like this. But what you can see over here, and what you can see over here, is they're kind of looking symmetrical, and we'll get to more of that later. Just dropping this right now, right? So that's our sample distribution. So one thing to note is that the mean of the sampling distribution is equal to the population mean, uh, which in this case is equal to 30. And this is always going to be true for unbiased statistics. And we'll get to what unbiased and biased is, but I want you to remember for most statistics, this is going to be the case, right? So let's go over the definition real quick. So sampling distribution is basically the distribution of all the sample means of all possible combinations of a sample of a specific size n from a population. The mean of the sampling distribution is equal to the population mean for unbiased estimates. The standard deviation is also known. So yeah, the standard deviation of a sampling distribution, uh, the sampling distribution that we just made, right? It's known as the standard error. Now you could calculate that, right? So we have one uh, 15, we have 125 to this. We could just, like, add them up and subtract them from the mean and do that typical standard deviation formula. But there's an easier way to go about getting the sampling distribution standard deviation, which would simply be, like, if we knew the population standard deviation, that's normally the population standard deviation divided by under root of n. That gives you the standard deviation of a sampling distribution. Right. And so when we get questions regarding sampling distribution, and typically we are asked to define a sampling distribution, we basically define it by determining its mean and standard deviation, also known as standard error. So standard error is the standard deviation of the sampling distribution, not a particular sample, but the sampling distribution itself. All right. So let's see. Let's look at this example real quick. Let's say we had a population of Americans with an average age of 22 and a standard deviation of 3. Let's describe a sampling distribution, of size 5. And I've written in the brackets what you actually need to do for this kind of question, right? So we know that the population mean is 22 and the standard deviation is 3. So what's the mean of the sampling distribution here, right? And what did we talk about, right? So the sampling distribution is every possible combination of a sample of 5 that we could take, and we just proved that the mean of every single sample mean is equal to the mean of the population. So our sampling distribution is going to have a mean of 22, right? So our sampling distribution is going to have a mean of, which is denoted by u of x bar, equal to 22, which is the same as the population mean, right? And it's going to have a standard deviation or a standard error equal to the population standard deviation divided by the root of n. And our n is the number of samples, which in this case we had 5. So that would be, we have 3 as our standard deviation. 3 divided by the under root of 5 would give us our standard error for the sampling distribution. And that's pretty much all we need to do to define a sampling distribution when we're asked to. Of course, we're not going to show every single, the frequency of every single sample and how many, all the different combinations and all that stuff, because that's too much work. Right. Moving on. So we have this term called point estimator. So a point estimator of a population parameter is a rule or formula that tells us how to use the sample data to calculate a single number. So basically, a point estimator is something that you use to estimate a parameter. So when we have a sample, right? When we had a sample of 5 people, and we knew that we got the mean as 22, the sample mean 22, you can say that if we're using it as an estimation of the population mean. So anything, any parameter or any statistic of a sample that you use to make a guess or make an estimation on the population is known as a point estimator. So simply put, the sample mean and sample standard deviation is a point estimator. All right. So yeah, I mentioned unbiased estimator. So basically, if the sampling distribution of a sample statistic has an average or a mean equal to the population parameter of interest, that statistic is said to be an unbiased estimator of the parameter. Otherwise, it is a biased estimator. If the statistic is not biased, the sampling distribution of the statistic is not equal to the parameter. The sampling distribution average of the statistic is not equal to that, then it's said to be a biased estimate of the parameter. Right. So what it's trying to tell us is that, uh, like in the previous slides, when we calculated that the means, the sampling distribution has, when the sampling distribution has a mean equal to the population distribution, that is a case of an unbiased statistic, meaning that there was no bias involved when selecting the samples. When this is not the case, that means there might be a bias involved with the samples we're selecting. So for example, like if we were calculating the mean age of the humans, human population, maybe all the samples that we were picking were from a college, and in a college there are typically more young people, so we're ignoring the old people population, and so there's a bias introduced in the way we're sampling. So when the when this property does not hold, this property that the mean of sampling distribution equal to population mean, uh, that's when we're dealing with an unbiased statistic, an unbiased estimator. All right. So let's move on to what I would say is one of the most important, uh, the important topics, or the most important theorems in statistics, which is called the central limit theorem. Right. So, uh, so what we talked about initially, right? Uh, we talked about this sort of sampling distribution, right? Where we took all the combinations of samples of size 2, uh, and we made a sampling distribution out of them, and it had sort of this symmetric thing, right? So, let's see. So, let's say we're taking the average age of every single human being, right? So that could be, we get the age of, right? Uh, so let's say we knew that the actual the actual mean age of uh, the human population is 30, right? So what happens if you take a sample of 5 people, right? 5 people, so they could have ages of 22, 23, 24, 25, 20, something like that, right? So what would we expect, right? So if we know that the average age is 30, we'd expect that our sample would typically be not too far off from 30, maybe not exactly 30, but not too far off from 30 typically, right? So let's say we took like 5 different samples, right? So one of our samples, let's draw a quick graph here. So we took 5 different samples. Uh, One of them had an age of or like 2 of them had the age of 30, right? So 2 of them had the age of 30. Uh, one of them had the age of 29. One of them was maybe 24. And the other one was, the last one was 34, right? Uh, Now let's say that we took 1,000 samples of this size. Uh, so, right, let's draw that again. So we took 1,000 samples, right? So this is 30. We're getting some samples from, let's say, 24 to 34. We're getting some samples over here. We're getting some samples over here. We're getting a lot more samples, maybe closer to 30, right? Because like if 30 is the average, our samples would be more likely to be around 30, and less samples here. So we get something like this, like 1,000 samples maybe, right? And so this is the case because 30 is the average age, so we'd expect our random samples to be close to 30, but we can get unlucky sometimes, right? Sometimes we pick like people who are aged like, maybe we took like a sample from an old home or something, or maybe we got like a bunch of old guys, right? So we end up with a sample here, but that's not super likely. That's why we get uh, uh, less people with high ages or very low ages uh, at the age of 30, less than 30, right? Uh, and we can kind of see that this is starting to somewhat look like a normal distribution. Maybe not quite there, but kind of approximately a normal distribution. So now, uh, uh, because we had a sample size of 5, right, it's possible that we get like an outlier or like a very old or a very young person multiple times in a row, and that's why one of our sample means is going to be high. That's why we get a decent percentage of our sample means above the mean and below the mean. Now, if we increase the sample size, let's say if we took a sample of 25 people or 30 people, right, and we get a thousand, like thousands of samples of those, think about it. When we have a large sample size, it's more unlikely to get a skewed result in our sample, right? So if we took 25 samples, uh, it's more difficult for us to get something that deviates too much from 30, right? Uh, because we're very likely to get ages around 30 and not that likely to get ages uh, too much that deviate too much from 30. So in this case, we'd have a sampling distribution that is less varied, right? And more concentrated around 30. So something, maybe something like this, right? This, and and now we can see that this resembles a normal distribution even more, which is pretty interesting, right? Uh, and and here's the fun fact, right? Your distribution, your population distribution might be extremely skewed. Let's say like uh, it might have a mean of 30, but it might have like a ton of older guys and like less younger guys, and maybe like extremely young guys with a smaller percentage, and like a lot of middle-aged guys. It might not be symmetrical. The population distribution doesn't have to be symmetrical. It might look something like this, right? But the sampling distribution, this is what the central limit theorem tells us, is always going to be normally distributed with a sample size that's large enough. So as the sample size gets larger, our population sampling distribution is going to be more varied, and it's going to be more of an approximation to the normal distribution. And what I'd like to do is, so there's this website that has a very useful visualization tool that can really help us see this in action, right? So what we have here, I encourage you guys to try this out on your own as well, but let's see. So what we have here is the parent population, uh, which we can set up, right? So I was talking about how our parent population does not have to be normally distributed, right? So let's mess it up a bit, right? Let's make it something very skewed, right? So maybe something like this, or I don't know, like maybe like like this, like something like this, right? So now very normal looking. Uh, and now let's take a sample of 5, right? So let me show you, like this also animates for us, right? So we took random sample of 5. Oh, sorry, I think I've set it to 25. So let's clear that. So let's set a sample of 5, take a sample of 5. We took 5 random values, right? We got the mean of that. We do it again. We took another sample, right? So now you can see that we're making our sampling distribution here. Took another sample of 5. We got that. We got that. So, and we can keep going, right? So let's say we took 10,000 samples. What is our sampling distribution going to look like, right? And it looks like a normal distribution. Maybe not exactly a normal distribution, but like a good approximation of the normal distribution. And we can see that by looking at the values here, right? So we have this thing called skew value and a kurtosis value. You guys don't need to know too much about it, but a skew value means how much a standard deviation has its mean skewed to either the left or the right, and how the kurtosis tells us that how much our standard deviation has a like it's like a standard deviation like with a smaller peak and more spread out tail as opposed to not like a typical standard normal distribution. So basically the closer these values are to zero, the more normal your distribution is, right? So what we can see is that our sampling distribution with a lot of samples ends up being very close to a normal distribution, but like with slight deviances from a normal distribution, approximately normal, right? Uh, so let's make another one, right? Uh, with a sample size, increase our sample size to 25, right? Take a sample of 25 here. Oh, sorry. Um, you take a sample of 25. We took a sample of 5 for this one and takes another sample of 25 for this one, right? And we can take again 10,000 samples and see what the sampling distributions look like, right? So as we can see, uh, so the sampling distribution that has more uh, is less skewed and has uh, less variance as well. So it's more normally distributed overall and it has less variance because the values are going to be less spread out, right? Like we discussed previously. So I encourage you to try this out yourself. It's like a very useful tool for visualizing and play around with the distant distributions. But this shows us the central limit theorem in action, basically. Right. And we can kind of see that here as well, right? We're increasing the samples, we're getting a distribution that's more precise, more normal, uh, and like for a distribution that was already pretty normal, it's always going to be normal, but less variance, right? And for more skewed distributions, you kind of need to increase the sample size more and more to get closer to the normal distribution. So typically we use a threshold of n greater than 30. So if your sample size is greater than 30, the sampling distribution will be approximately normal. Perfect. And here are a few notes, right? So the greater the skewedness, as I mentioned, the larger the sample size we're going to need for approximate normality. Uh, and usually we consider the benchmark of n greater than equal to 30 to be sufficient enough to achieve approximate normality of the sample mean. Perfect. Uh, and means of random samples are less variable than individual observations, and means of random samples are more normal than individual observations. So what this means is that our sample distribution is going to have a standard deviation, right? A variance that is less than the population. So you can kind of see here, right? So this was a normal distribution with a high standard deviation, like high variance. And the more samples we take, the less variance we have. And that plays well, like makes sense, right? Because our formula for the standard error, which is the standard deviation of the sampling distribution, is basically population standard deviation divided by the number of samples. So the samples increase, our variance decreases. Makes perfect sense. And yeah, that's about it. Uh, here's a sample. Here's an example that you guys should try out, right? And in fact, let's do this example right now. So the College Student Journal investigated differences in traditional and non-traditional students, where non-traditional students are generally defined as those 25 years or older. Uh, Based on the study results, we can assume that the population mean and standard deviation for the GPA of all non-traditional students is mu equals to 3.5 and sigma, the standard deviation, equals to 0.5 respectively. So part A, what is the approximate probability that the sample of 100 non-traditional students has a mean GPA that exceeds 3.62, right? Now, it's talking about the approximate probability that the sample of 100 non-traditional students, right? So there are so many ways you can take the sample, right? It could be any sample of 100 non-traditional students. And we've been talking about sampling distribution right now, right? So we also know that a sampling distribution is normally distributed, especially for values greater than or equal to 30, right? So we know that the sampling distribution we're going to get is a normally distribution. It's not a very good normal distribution diagram, and it's going to have a mean that is equal to the population distribution, right? Which we already have. So our standard, our sampling distribution has a mean of 3.5. Now the question is asking, what is the probability that the sample of 100 students has a mean that exceeds 3.62? So we want to know what our probability is that we are greater than 3.62. Somewhere here, like we don't know exactly what part, but like basically this area, whatever portion of the sampling distribution, whatever percentage of the sampling distribution lies beyond 3.62. So how do we do this? I mean, I'm assuming that you guys have already studied how to solve normal distribution problems, so it's very similar, right? So we calculate the z-score, which is basically how many standard deviations are we is 3.62 away from 3.5. So what is our standard deviation? Uh, Make sure to not make the mistake of assuming the standard deviation to be 0.5, because this is for the population, not the sampling distribution, right? So for the sampling distribution, it's this population standard deviation divided by the root of the number of samples. So 0.5 divided by the root of 100, which is 10, which is 0.05. So 0.05 is our number of standard deviations, which is 0.05 is our standard deviation for the sampling distribution, or standard error, right? Uh, Now, to calculate how many standard deviations we're away, we're simply gonna do 3.62 minus 3.5 divided by the standard deviation, 0.05. And what does that give us? 0.12 divided by 0.05. And that gives us 2.4 standard deviations. That is correct. That is indeed correct. So 2.4 standard deviations away, right? Right. So now we know that 3.62 is 2.4 standard deviations away. So now we can just use the z-score table, the z-table, to calculate our probability. So let's have a quick look at the z-table. Let me pull that up. Right, so we have our z-table here, and the number of standard deviations 3.62 was away was 2.4. So let's look at 2.4. 2.4 gives us 0.9918 with to the left, right? And we want to know the proportion of values greater than 3.62. So we're gonna take this proportion, right? So we minus this number from 1, right? So 1 minus 0. Look at that again. 1 minus 0.9918, 0.9918. That gives us a very small number, right? So 0.0082%. So only 0.0082% of the sampling distribution values, the portion of the sampling distribution, lies beyond 3.62. So that is our answer, right? So it's basically a normal distribution question, but we just got to remember we're dealing with a sampling distribution, so we make sure that our standard deviation is the correct one, the standard error basically. Perfect. So there's our answer, right? So let's look at part B real quick. So if your random sample actually produced a sample mean of 3.62 or higher, right? So you're saying we got a sample of 100 students and it had a mean of 3.62 or higher, would you consider that unusual? And what conclusion might you draw? So basically, he's saying so we know that the probability of getting something higher than this is very low. It's extremely low actually, 0.0082. So we're very probably extremely unlucky in getting that. So because it's very unlikely, it is an unusual result. And the conclusion we could draw is that either we got extremely unlucky with our sample, so it's a bad sample, or the our population parameters may not have been that accurate. So it's two ways of looking at it. And that's about it.